Hey everyone, in this video I'm going to be showing you a closer look at my all alcohol fuel stove and talking about why it was designed the way it was designed. The burner cup is two stainless steel condiment cups. They sell these things for putting ketchup and things in. The top portion of a larger one is affixed with these screws to this bottom one. I found it was necessary to do that to raise the impingement plate higher up off the orifice, or it wouldn't work properly. The impingement plate is a circular piece of stainless steel with a slight dish shaped bent into it. These three arms are stainless steel wire. There are three stove legs / pot stand arms. They've been incorporated into their own separate units here. They attach to the stove with this triangular piece here. There's three corners on this triangle. Each corner of the triangle has a slight downward bend, and combined with the angles and bends of this sort of intermediate piece, that allows these pot stand arms and stove legs to fold up and into the side. Perhaps it's easier to see this way, how as the entire arm is rotated, it rotates in towards the stove and also up. The legs fold in along the side and the pot stand arms swing around behind the whole thing. The fuel line is a silicone fuel hose. It's for gas-powered radio-controlled models. This outer stainless steel braiding is actually a sort of performance accessory for the very same application. I've terminated the ends of the fuel lines with a short piece of stainless steel tubing to act as a thermal barrier between the brass vapor generator loop and the silicone rubber hose. Silicone withstands heat better than most other materials that can be used as fuel line, but still I was worried about a heat failure here because this is under pressure with a flammable liquid inside. I've joined the fuel line to the vapor generator loop. These are both 1/8 inch diameter with a 1/8 to 1/8 compression coupler. Where the vapor generator here enters the orifice elbow, I have one of these same fittings. However, I tapped the elbow to 5/16 24, which happens to be the same thread or almost the same thread as this here. So then one of these fittings can be threaded into the elbow, and then the vapor generator joined to it with the compression fitting here. Early on, what I had done is I had taken one of those fittings and cut it in half, giving me two pieces that were like this. You have the compression nut here and the other end of the compression fitting, and I had this flat surface here just soldered onto the elbow. which sort of gave me this similar arrangement. However, the heat from operating the stove was actually enough to melt the solder joining this. Luckily that didn't happen while the stove was running. It happened after I shut it off and the heat sort of soaked around and loosened up that connection. So one of the design challenges was the fuel delivery and vaporization system couldn't have any soldered connections. This is problematic because of the heat, because what else can you use? You can't use epoxy or anything like that. So all connections in this hot area have to be threaded or a compression fitting, some sort of mechanical way to join them together. Here you could see the impingement plate. Originally, the arms that held the impingement plate in the center of the burner bell were an integral part of the centerpiece. They were just wide, flat stainless steel arms that came out. I found out that blocked a lot of the flame, which I felt was kind of inefficient. So I opted for this stainless steel wire method. That sort of gold colored piece underneath is a brass nut, which I have filed 3 grooves into, which locate those stainless steel wires. And then the smaller stainless steel nut on top is tightened down and it holds them all in. Here you can see the very slight dished shape to the impingement plate. That's very necessary for a proper burn. I noticed a flat impingement plate barely worked, and the dished shape, if used upside down, would not work at all. So this very gentle dished shape is important for the proper function of a burner like this. Inside you can see where the vapor generator both enters and exits one of the combustion air holes in the bottom of the burner cup. This vapor generator is built out of a 3-foot long section of 1/8 inch diameter brass tube. I found out it's important before attempting to try to make these kinds of bends in the brass tube is to anneal the brass tube first. The vapor generator begins by entering the cup and coming up and around about 5 times before exiting out the bottom. In the bottom surrounding the orifice is a donut of carbon felt. This is to absorb fuel for priming, and it kind of keeps the priming process under control. Before adding this carbon fiber wick, it was just an empty space in there, kind of like a priming pan. And that was problematic. When I would prime the stove, the priming fuel would begin to boil and it would shoot little flaming droplets of fuel out of the combustion air holes here. So the carbon felt kind of prevents that from happening by holding on to the priming fuel while it's burning. The orifice diameter in this stove is 0.024 of an inch. It's significantly larger than a liquid petroleum orifice. You can see there's quite a bit of that smut from burning isopropanol in there during priming. When the vapor velocity out of the orifice is sufficient to support the proper burning, it burns very clean. In 3 spots around the top of the vapor generator, I have the vapor generator sort of staked down with a washer and a stainless steel screw. There's just a nut on the other side. The Orifice plug is of the hex top variety, and the hex top allows the plug to also function somewhat like a bolt, and that's how the burner cup is held down to the orifice elbow. The vapor generator loop is actually constructed out of a 3-foot long section of 1/8 inch diameter brass tube with a slightly smaller diameter 3-foot length of brass tube that slid just inside of it. This was done primarily to give support and strength to the vapor generator loop, as well as reduce the empty volume inside. I had previously attempted to make vapor generator loops out of 1/4 inch copper and brass tube, and found that the amount of fuel that could fit inside a 1/4 inch diameter tube was much too much than you want to be in there. If you are building a vapor generator, you need to remember that all of the fuel that can fit in the vapor generator loop must then be vaporized. And if you can fit a lot of fuel in the vapor generator loop, it's going to be difficult to vaporize it all. It will likely shock the vapor generator loop, as in very rapidly suck all of the heat out, and the vapor generator loop can't keep up, and suddenly you get liquid squirting out of your stove. So I found it was important to minimize the amount of fuel that could fit in the vapor generator loop, because the vapor generator loop can only vaporize fuel so fast. Another thing to reduce the empty volume inside is there is a small strand of copper wire crammed down inside. I found that this copper wire crammed inside helped the performance dramatically. Without the copper wire, it barely worked. It sort of worked, but I wasn't happy with the way it would sometimes squirt liquid out. With the copper wire crammed in as far as it would go, which ended up being about almost one complete turn around the first loop. The copper wire doesn't go through the entirety of the vapor generator loop. I was only able to get it to come to about here. But that helped the performance of the vapor generator dramatically. Doubling up the 2 nesting tubes also helped provide some support for when tightening down a compression fitting. Normally with a compression fitting, there is some type of separate support piece that is placed inside to prevent the compression from crushing the tube. Since no such thing exists for tubing this small, doubling up the thickness of the tube also helps provide support for the compression fitting. The fuel bottle is a stainless steel vodka bottle. Unfortunately, I don't know if these are available anymore. I found this stainless steel bottle to be a much better choice for a fuel bottle than like an aluminum water bottle. Obviously, it's much stronger being stainless steel. Corrosion resistance, which is important for reasons I'll get into later, and the threaded section here is a very high quality. It's a nice deep threaded section. The fuel bottle pressure pump is built around an aluminum flashlight. This green plastic piece is actually an adapter for adapting a sprinkler valve of some kind to pipe threads. If you have a water bottle like this, or one of these bottles, they all have the same thread, and this thread is actually a common 3/4 pipe thread. So any common 3/4, PVC pipe thread fitting will screw right into it. I chose the sprinkler valve adapter not because it was green and matched the flashlight, but because the inner diameter fit the outside bore of this flashlight much better. Along the side here you can see a short piece of silicone tubing with a stainless steel nut just crammed over the outside at the end. This acts as a weight, or how they are referred to in gas-powered radio-controlled aircraft, this is referred to as a clunk. This is how the fuel is collected from fuel tanks in radio-controlled airplanes. And they use this so even when flying upside down, the gravity will pull the clunk to wherever the fuel is, because both the fuel and the weight get pulled to the same place. Passing through the threaded plastic piece in a small brass tube, it ends at a needle valve. This needle valve was salvaged off of a gas-powered radio-controlled model's engine. This needle valve originally was for adjusting the fuel-air mixture of these engines. And so, quite amusingly, at least to me, that this needle valve, which I've repurposed, is actually doing precisely what it was designed to do. The fuel in these gas-powered models is primarily alcohol, with some natural oils and nitromethane. So this needle valve was designed to very precisely meter the flow of alcohol fuel, which is what it's doing here. On the end of the needle valve, I have attached a half section of one of those compression fittings. Taking a look at the pump plunger or pump piston, it's really quite simple. It's just a piece of 1/4 inch stainless steel tube with this rubber washer on the end. Behind the rubber washer I have a stainless steel washer to give it support to prevent it from deforming under pressure. The stainless steel tubing allowed an easy attachment point, as I could just tap the inside with threads and run a screw in. However, this did provide a leak path all the way through the center of the shaft, so the threads had to be sealed with something like Loctite. Attached in the same way as the rubber gasket, I have the top sort of handle or knob. This particular piece I've had in my junk drawer for quite some time, and it's some sort of bicycle component. Either this is the top cap of the headset, the thing you'd find sort of in the center of your handlebars, or part of a pivot bearing assembly for a full suspension bike. I can't remember which. It's not too terribly important what this is. You can screw anything you want onto the end if you make one of these. It could just be a plastic knob. Through the flashlight's battery cap, I have drilled a hole that is slightly larger in diameter than 1/4 inch. The shaft actually rides on a nylon bushing which I have pressed into a counterbore that I drilled into the battery cap. And here you could see how the stainless steel pump shaft doesn't actually contact the aluminum battery cap, which makes for a very nice smooth operation. And then you come to the one-way valve assembly. Into the end of the aluminum flashlight, I have placed this rubber grommet. And what seals against the rubber grommet is this high-density polyethylene ball. It's not like I had a wide variety of materials to choose from for making this sealing ball. Well, I didn't make it, but this sealing ball needs to be very smooth, so you're looking at plastic or metal or glass. High-density polyethylene is a good choice since it's nice and lightweight being a plastic, but it's very chemically resistant. They make gas cans and fuel containers out of high-density polyethylene, as well as milk jugs, but it's very resistant to solvents and chemical attack. In what used to house the reflector and lens is where the retention spring is. This spring is stainless steel to resist corrosion, and it is held in place in the same way the lens of this flashlight was held in place. You may be thinking to yourself that I'm missing my other one-way valve. There needs to be two. And you're right, if I pull back on this plunger and let it go, it sucks back in. And there doesn't seem to be any way to let air into the pump. This one-way valve lets air exit the pump and resists pressure from the fuel tank from escaping through the pump. But how does air get into the pump? And that is accomplished simply by retracting the plunger all the way back. And what happens is that rubber gasket gets pulled out of the flashlight bore into where the inner bore enlarges for the threads. So what that allowed me to do is omit one of those one-way valves. There is only one valve. Fortunately, that allowed me to keep this pump design very simple because I didn't want to figure out how to make a second opposing valve to make this work like a traditional pump. Originally, I was thinking I was going to have to somehow incorporate the second valve into the pump shaft. It would draw in air through the shaft and push it out the end of the pump. One disadvantage to this bottle is it wasn't designed to hold pressure, and it can hold quite a bit of pressure, but I managed to bulge the bottom of this thing out so now it won't sit flat. The reason why I don't want to use aluminum as the fuel pressure bottle material is that during the development of this stove I found out that methanol is corrosive to aluminum. I had left this pump installed on the fuel bottle for a lengthy amount of time with fuel in the bottle. And when I opened it up, there was a white chalky material all over the exposed aluminum parts of this flashlight. The damage wasn't serious, but still it was perplexing until I figured out that methanol was corroding the aluminum, or the aluminum was reducing the methanol. I'm not exactly sure what the reaction is, but bad things are happening. So for storage, the pump is not carried on the fuel bottle. I know that kind of sucks. That was my plan to begin with. But in carrying the stove, the pump is carried uninstalled just like this, and the fuel bottle with a standard cap on it. If I had used a water bottle that was made out of aluminum, or even a standard white gas stove fuel bottle, which are also typically made out of aluminum, that would have me very concerned, because this not only is very thin, this is what's holding the pressure when the stove is in operation. If the flashlight body gets a little corroded, I don't feel that that's a serious safety concern, but I don't want my fuel eating away at the inside of my pressurized bottle. Another unfortunate property of methanol I discovered is it is very good at destroying epoxy resins. Other people have used epoxy resins like JB Weld and whatnot in building alcohol stoves, and it's worked, but in my usage and my performance requirements, the epoxy would degrade at an unacceptable rate. And so not only can I not solder connections on the vapor generator loop, not use aluminum for the pressurized bottle, I also cannot use epoxy on anything that contacts fuel. All of this epoxy up here doesn't contact fuel because the brass is sealed to the needle valve before the epoxy is put on. The epoxy was put on just for strength. The actual liquid seal is accomplished with Loctite. The flashlight, once put into place inside the PVC fitting here, this gap is sealed with super glue, of all things. I found super glue holds up quite well to alcohols. But as you know, super glue is not good at filling gaps like epoxy is. So there couldn't be a large gap here. Hence why I use this fitting as opposed to just a standard white PVC fitting, which has a larger inner diameter for some reason. So that's this stove in a nutshell. It's kind of unbelievable at this point that it took so long to figure all these things out. Now that I've done it, it kind of seems obvious, but that wasn't the case a few years ago. I know that this isn't particularly interesting to everyone, but I felt it was important I talk about how it was designed. Otherwise, it's, just a video showing off something I made. So I hope you learned something, and I'll catch you in the next one.